All right. So we're doing internal loads. Um, and what we were doing so far was we had this body that was like, well, let's see. We had a pin over here, a roller at the other end. We were ignoring the weight, and there was a 1,000 Newton force here. The whole thing, I think, was 1 meter long. Yeah. Yes.
About breaking this up into multiple pieces.
Yeah.
And then doing that piece to get like a load at each point. Would that be calculus? Because it sounds like very much like calculus, like breaking it up into teeny tiny
Yeah. Well, yeah, it does sound like that. Mostly, it's we're not going to, although we will see. You can approach it that way, and we will see a little glimpse of that. But mostly, um, we're just gonna we're gonna represent things in terms of variables and come up with formulas. But yes, that is kind of the idea. Is like we did this calculation for we calculated the internal loads here last time, but if you're looking at a beam, you don't want to know the internal loads at one single spot. You want to know them everywhere. Um, and you could just, like, one thing you could do is, write a computer program that does this at 100 different spots and see how it varies. That might be okay. But we're gonna find a way to do that calculation continuously. Okay. So now what we want is to know the internal loads at all points along the beam. Okay, so I said one way to do it is to do 100 different calculations. I mean, you could do it by hand, it just takes a long time. But let's think of what it would look like to calculate the internal loads at a bunch of these different points. Okay, so what would it look like uh, to calculate the internal loads at multiple locations? Um, well, let's start thinking of free body diagrams for different points. Okay. So let's think of the free body diagrams for various cuts. Okay. So first of all, imagine that we want to calculate the internal loads very close um, to the left edge, to the left end. Okay. So the the light blue is all the stuff that's not going to be included in our free body diagram, and the black is the stuff that is included. Move it down a little. Okay. Um, so what loads are acting? From the external load calculation before, we knew that this is a 500 Newton force up. Okay. And there's a 1,000 Newton force in the middle, but that isn't acting on our piece. So I'm doing that in the light blue. So, I mean, that's out there somewhere, but it's not acting on the piece that we're thinking of.
Not at all.
No, it's acting on other stuff. So with each one of these cuts, we're just choosing part of this body to be our chosen system. Okay. And then there's also another 500 Newton force here, but that's not acting on our piece. And then what else is acting on on our chosen piece? There's the internal tension T, the shear force V, and the bending moment M. Okay. Well, that would be to calculate the internal loads at the right end of that little sliver in black. Okay. So now let's think of another location where we want to calculate the internal loads. So now we're going to do all of this. All of this is external to our body. So on our chosen piece, we have a 500 Newton force. Not acting on our chosen body, we have the 1000 here and the 500 here. And then also acting on our chosen piece are the internal loads. So we have a tension, a shear force, and a bending moment. And I'm going to do one more before we get to that 1000, just to totally belabor this point. So we have the 500 here. The 1000 is not acting on our chosen body. Bless you. And this other 500 isn't acting on our chosen body. And then we have our internal loads T, V, and bending moment M. Okay. And now we're going to go, I'm going to do one where we're calculating the internal loads to the right of that 1000 Newton force. Okay. We're just little by little making our chosen pieces bigger. Okay. So this time we have a 500 Newton force here. And this time the 1000 does act on the chosen body. The 500 over here still doesn't. And then we have our internal loads T, V, and M. Okay. And I'm going to do one more of these. So now we're going to go, the piece we're going to isolate goes almost all the way to the end. We just have a little bit that's not included. So now we have 500 here, 1000 here. We still have 500 here that doesn't act on the chosen body. And then we have the internal loads. Okay, so notice that the first three I did are all like qualitatively the same. They have the same loads acting on them. Okay. So these are the same free body diagram qualitatively. Okay. But then once we get to that 1,000 Newton force, that's not true anymore. Like any one of these could be a stand-in for the free body diagram for any of the other ones. But that changes once we get to that 1,000 Newton force. And so these two are qualitatively the same free body diagram. You know, same FBD qualitatively.
The internal are, when you did the calculation, would the internal loads be different?
Yeah, the internal loads will be different, but just the look of the free body diagram, what loads are drawn in your free body diagram are the same for all the things before we get to that 1,000, and they're the same after. Okay. And so our approach is going to be, our approach is to do one free body diagram for each group of pieces that are qualitatively the same. And distances from these things matter. So the way we're gonna, what we're gonna do is we're just gonna say, so these three free body diagrams are the same. It's just that the length is x, and x can stand for anything between 0 and where that 1,000 Newton force acts at the 0.5. Okay. And then that's going to represent the internal loads all the way from the left end to the middle. And then once we get past that 1,000, we're going to have a free body diagram that looks like this, where we're going to represent the length with an x. And those will represent everything from the internal loads for everything from where that 1,000 Newton force applies all the way to the end. Okay. So we're just going to do it with a variable now. But we're going to have to do, you can't get past the fact that these three are just not the same thing as these two. Okay. Okay, so let's do it. So our cut 1 is going to be valid for all x's between 0 and 0.5. You guys all seen this interval notation? Jeez. So this is saying this is only valid for x's between 0 and 0.5. And I'm just going to draw like one representative cut. And we have a 500 here. We haven't gotten to the 1,000 yet. And then we have the internal loads T, V, and M.
And you need 0.5 because the whole length is 1, and that's where the 1,000 happens.
Yes, right, exactly. So, so the length of this thing now, it isn't like when we did the one specific example last time, the length of the beam was 0.25, you know? but this has to represent a whole bunch of lengths. So we're just going to call this x, and we're going to get our answers in terms of that x.
And for the 3-bus diagram, you draw like whatever you want, like whatever length.
Yeah. Yeah, just somewhere in the middle. But so notice that if this x is equal to 0.05, say, then that'll give us the values for this little tiny piece. And if that x is 0.25, it'll give us the values for this second piece.
So would it have to be just less than 0.5, because that 0.5 isn't the 1,000 newtons, or
Right.
1,000
Exactly. It has to be less. So in this interval notation, notice that's like a soft bracket because it doesn't, this can't represent the point where that force acts, but it can represent anything right up until before, 0.49999. Okay, and let's do these calculations. So I'm gonna keep doing the table for now. Eventually we'll do it a little quicker way, but all we're doing is a rigid body statics for this piece. So this table works perfectly well. And like always with these, I'm gonna have my about point over at the left end. It's just gonna make the math simpler for these. So first, the 500 Newton force. The row vector is 0. The force is 0, 500. The moment is 0. Then I'll do the force T. That row vector, okay, so where is that force T acting? This distance horizontally is x. So if you wanted to represent that row vector as, in components, it would be x0. The force is T0. Cross product is 0. Then V. That's acting at the same location, so the row vector is x0. That V is in the negative y direction, so this force vector is 0, negative V. And so the cross product is negative Vx.
So even though V is acting like down, we don't care about the right direction for the row. And we don't have any information to know that, so we just don't.
Oh, yeah, we're assuming that this doesn't have any significant thickness.
Okay.
So, yeah, so we don't care where it is vertically. And then the last one is the bending moment. We don't, for couples, we don't care about row vectors or forces. And so this just comes out to be M. And so Newton's second law says 0, 500 plus T0 plus 0, negative V is equal to zeros. And so if you solve these, this tells us that T is equal to 0 and V is equal to positive 500. So for any x value, that's what the internal tension and the internal shear force is. But then for the moment, it's going to be different for this example. So add up all the moments and set them equal to 0, and we get that negative Vx is negative Vx plus M is equal to 0?
We know M is equal to 500x.
Yep, that's right. So m is equal to Vx, and then we already calculated V, so m is equal to 500x. Okay. So now the way this works is if you plug in x equal to 0.25, you'll get the answers that we got last class when we just looked at that one piece. Okay, so plug in 0.25, you get t equals 0, v equals 500, and m is equal to 125. And here, let me just show this for a second, Mira. Okay, so those are the answers that we got last class.
So the tension force and shear force don't depend on X.
They don't in this case. Sometimes they will, but not yet. Okay, so these are valid. And I'm going to call these subfunctions. Anyone remember the term subfunctions when you saw those? So I don't know if they described it that way, but a subfunction is like when you have piecewise functions with the curly brackets, and you have like this function is equal to f of x is equal to x squared for x equal this to this, and it's equal to negative x for x equal this to this. Remember doing that in maybe algebra 2 or something? So those individual functions inside the piecewise function, the set of piecewise functions, are called subfunctions. And that's what these are. So these subfunctions are valid for x in the interval from 0 to 0.5. But they don't tell us anything about the internal loads for x's between 0.5 and 1, So now we have to do those. Are you with me? And the reason they don't is because the free body diagram that all of this is based on doesn't represent these cases, So now we need a representative free body diagram for the second half. So now we're going to go to our cut 2. So this is for x's between 0.5 and 1. And a representative free body diagram looks like this. We have 500 here, 1,000 here, and then internal loads.
What happens to the other 500?
Yeah, so we're only considering the cases up until right before you get to that 500. Okay? This.
Like the whole like one. And we're looking at X.
Yeah, but what this is saying is x is between just over 0.5 to just less than 1. That's what this represents. Okay, so it doesn't tell us anything at that actual point where all the way at the right end. Okay, and that's how we're always going to do these. Okay, and let's think about the distances to things. Okay, so this distance, the distance to the end of this piece is x again. Okay, it's just that x stands for different numbers this time, a different range of numbers. What's this distance? Yeah, 0.5. So no matter what x is, the distance from the left end to that 1,000 doesn't change. Okay. And now I'll do the table. My about point again is going to be at the left end. So I'll start with the 500. Row vector is 0. Force is 0, 500. Cross product is 0. Then this time we have the 1,000. What's the row vector for the 1,000? 0.50. Because it's just, you're just going in the x direction and we're not worried about y. So this is just 0.50. And the force is 0, negative 1,000. Cross product is negative 500. And then we'll go to t. That row vector is x0. The force is t0. Cross product is 0. Then v. Row vector is x0. The force is 0, negative v. Cross product is negative vx. And then last is the bending moment. We don't care about row vector or force. And the couple has a moment m. So Newton's second law says 0, 500 plus 0, negative 1,000 plus t0 plus 0, negative v is equal to zeros. And this time, well, we still get the same internal tension. T is equal to 0. The shear force is this time negative 500. Last time it was positive 500. And now the moment equation. So we have negative 500 minus Vx plus m is equal to 0. So m is equal to positive Vx plus 500. And so m is equal to negative 500 x plus 500. And so now these subfunctions are valid for x's between 0.5 and 1.
Or what's if x is equal to 0.5? Or x, like, cause then which one do you use?
Well, so yeah, that's a good question. Sometimes they agree on the value, you know, but the truth is, and so I guess then you would just use where they both converge to. But sometimes they, you know, going from the left it goes to a totally different, approaches a totally different value than going from the right. I think the answer is we just don't know exactly what's happening at that load. Remember that point loads are always approximations of what's really happening anyways. Every load is distributed somewhat, you know. So what does it mean, the internal loads exactly at a perfect point force? It's not very meaningful to us, you know. Yeah. Okay, so let's write these values.
But you
Yep.
never ask us like find it at that point.
No, really, I just ask you for these piecewise functions.
Okay.
And we'll just kind of think at the points where these subfunctions change, we don't exactly know what's going on, you know. So we'll only think of what these values are as you approach from one side or the other side, that kind of thing.
Why we never reach like to like one, like to
Yeah, well, it's the same reason, really, because what's happening at one is there's this point force happening, you know. Yeah, we'll just think of it as like we can see what it's approaching, but remember when you did that stuff with piecewise functions many years ago? You would do these graphs that had little open, like hollow circles. Yeah, that just shows like I don't know what's going on there, but you know it's not a big concern. Actually, mathematicians, it is a big concern to them. It keeps them up at night worrying what happens at that circle. But to us, like, we're like, okay, what happens a millimeter from the circle? What happens half a millimeter from the circle? Like, that's good enough, you know. Let's not sweat it. Okay, so let's write these out as piecewise functions. So you can think of like t as a function of x then is equal to, well, this is equal to 0. Doesn't change. Okay. For all x from 0 to 1, not including the two endpoints. The shear force, this is a piecewise function, and it was equal to 500 for x between 0 and 0.5. Okay, and then it was equal to negative 500 for x between 0.5 and 1. And then the bending moment was also a piecewise function, and it was equal to 500x for x values between 0 and 0.5. And it was equal to negative 500x plus 500 for x values between 0.5 and 1. And you can plot these piecewise functions out to get a sense for what these look like. Okay. So if you graph the internal tension as a function of x, it would just look like this. That's pretty boring. I didn't put any horizontal stuff in there, so there's no tension or compression. If we plot the shear force as a function of x, so here's our 0.5 and here's our 1. And here's 500 and here's negative 500. We get this for the first half. This for the second half. Okay. In a math class, you would do both of these as open circles, and you would do an open circle at the end. But just to absolutely infuriate the math people, because we think it's a little funny, we just connect them with a vertical line. They'd be like, a vertical line on a function, like they'd freak out. But yeah, sorry, that's how we do it. Yeah, right. I mean, we'll see all sorts of different shapes of things, but whatever. That's how engineers have always done it, so that's how we're going to keep doing it.
And pi is 3.
Yeah, exactly. Okay, and then for the bending moment, bless you, 0.51. So this would look like, so it's going to go up to a maximum of 250. And then go down to 0 from there. So you get a function like that. And so, can you tell anything useful from this? Well, really, the most useful stuff you can get out of an analysis like this comes from using this to calculate stresses and strains. Excuse me. But you can see actually in this simple case, you can see like, okay, the tension is the same everywhere. The magnitude of the shear force is the same everywhere except for whatever is happening right at that point force. Okay. But the bending moment goes up to a maximum absolute value right at that midpoint. So since there's no change in the tension, the only difference in the shear force is right at that point force, we could say from this that we're most concerned about this beam breaking as you get closer and closer to the middle of the beam. Okay. You can't always figure out stuff like that from internal loads, but in this case, you can. And so you might say like, okay, we need to beef up the middle of the beam or give it some kind of support or something that changes the profile of those internal loads.
So can you look at that graph and figure out at what amount of newtons it's going to break?
No, you cannot. But if you use this to calculate stresses and strains, then you can start to answer that question. Yeah. Okay, two things. Yeah.
So the 250, where did that come from?
That was just plugging values into these functions. Yeah. Okay, I said two things. What are they? One of them is, so one, I don't know. Okay, I have one thing anyways. So this is one very important fact that we're going to use all the time. At every x value, the derivative of the bending moment with respect to x is equal to the shear force. Okay. So as we get into more complicated problems, we'll use this as like a check on our answers, you know. So if you mess something up in the middle, a lot of times this relationship won't hold, and then you'll know something went wrong and you can go look for it. Okay, any questions? All right, so yeah.
Is there a way to use what we've done for trusses and all this in integration form rather than just piecewise functions?
Yes, yes. And it turns out that this is always as quick as doing like using an integration approach, but you're exactly right. This is like a law, and you could use this to calculate this stuff the same way. You know, as we get a little farther into it, maybe we'll do an example where we do it once, and you can see why it just gets messy and complicated. And I think it's better for us to just go through. We're going to do the calculations this way using free body diagrams and stuff. And then we'll use the derivative relationship as a check. Okay. So next time we'll start looking at this with distributed loads. Oh, I know what the other thing was I wanted to say. Yeah. So this is important too. Where do the subfunctions change? So where do you have to change to a new cut? So yep, point forces are one of them. Point couples are another one. And then the last one, we haven't done distributed loads with these yet, but the third place is where the distributed load function changes. So where the distributed load function changes. So if there's a spot where the distributed load goes from a, from like a diagonal line, like a triangular distributed load to a uniform distributed load, at that point where the function changes, you have to change to a new cut. Okay, that's all.